Hi there! This video covers every single Python NumPy function that exists. This is the agenda. It can also be found in the description. First, it will start off with a video that introduces you to NumPy and covers all of the basics. Then, the video will show you detailed explanations of many NumPy functions, separated into categories of creating, combining, splitting, slicing, manipulating, importing, exporting, and finally, it will finish off with some additional NumPy functions, including the polyfit method. Let's get started. In 2005, Travis Oliphant changed the world because he invented NumPy, the amazing package that makes Python the best. NumPy is Python's package that lets you create arrays. And to use it, all you have to do is import NumPy as np. That's what everyone else does. And to create an array, you simply type np.array, parentheses, and then you create lists of lists. So we'll do a list of 1, 2, 3, a list of 4, 5, 6, and we'll finish it off with a list of 7, 8, 9. 7, you cannibal! The way these arrays are organized makes me so happy because you can access any element that you want inside of the array. Let's talk about indexing. The way this array is organized is bracket, row, comma, column, and you'll see what I mean. The first row is accessed as 0. The second row is 1, and the third row, you might have guessed it, is 2. So if we want an individual row, all we have to do is call that row's number. So A of 0 is going to be 1, 2, 3. A of 1 is going to be 4, 5, 6. And A of 2 is going to be 7, 8, 9. If you want a column, the first one is colon, comma, 0. The second one, colon, comma, 1. And the third, colon, comma, 2. Now, why do we need that colon? That's because, as we saw at the beginning, you enter the row first. So if you want the entire column, you do colon, comma, column number. Just like that, colon, comma, column number. The first column, colon, comma, 0, will be down the column, which is 1, 4, 7. The second column, be colon, comma, 1, which is going to be 2, 5, 8. And last, but definitely not least, colon, comma, 2, which will be our 3, 6, 9. Now, of course, you don't have to just access an entire row or column at once. You can access the individual elements. So for example, across the diagonal, you want that first entry in the diagonal, it's gonna be row 0, column 0, so 0, comma, 0. The 5 in the diagonal, similarly, row 1, column 1, 1, comma, 1. And last, that 9, row 2, column 2, boom, 9. And of course, we can fill the rest of these in a very similar fashion. And if you notice, going across the row with our row 0, the first entry in every element in the first row begins with a 0. And in the second row, they all begin with 1. And in the third row, you guessed it, they all begin with 2. Now down the columns, we see the same pattern. The second entry for those elements in the first column is 0. The second entry for those elements in the second column is 1. And the second entry for those elements in the third column is 2. And we can use this to access any tiny little element that we want. So for example, if we type in A 0, comma 0, that's gonna give us our 1. If we type in A of 2, comma 1, that will be row 2, column 1, which is 8. And if you type in A of 0, comma 1, which is 2. I think you're starting to catch on. Now, let's talk about shape. As you can imagine, these arrays have a shape to them. Yeah, that's right, number of rows and columns. So to access this shape, it's really easy. All you need to do is type a.shape, and it will give back a tuple of the number of columns, comma, number of rows. You can also do the exact same thing by doing np.shape of your array. We present to you today's broadcast, grabbing whatever part of the array that you want. Now, we've already touched on how you can grab individual rows, columns, or even elements inside the array. But what if You want to grab a tiny part of a column, or the corner of the array, or the tiny matrix that's inside of your array. Well, array broadcasting is going to be what helps you out. So the syntax is very similar to the indexing we were doing earlier, meaning that the row and column are still separated by a comma. To broadcast the specific part that we want, we will have a start::stop for both the row and the column. Now keep in mind, whatever you put as the index for stop does not actually include the stop. So it's always up to, but not including. I think an example will help you out. So here's our array A. And let's say we're not interested in all of A. We just want its money. We just want 4 and 5, meaning those two elements right there. NumPy makes grabbing those effortless. So starting with the row, this begins at row 1 and ends before row 2. Now over to the columns. This begins at column 0 and ends before column 2. So if we want to get just that 4 or 5, we simply type row 1, colon 2, column 0, colon 2. And by the way, you actually don't need to put that 0 because NumPy assumes you're always starting from the beginning. So you can admit that and it will give you the exact same thing. Let's look at this in code. So A of 1, colon 2, comma 0, colon 2 gives us an array of just 4, 5. And if we omit that 0, 1, colon 2, comma, colon 2, we equally get 4, 5. Let's jump into another example. Say this time you just want the corner 4 elements. Or in other words, 5, 6, 8, and 9. Again, from the top, the row begins on row 1 and the row ends before row 3. The column begins on column 1 and it ends before column 3. To grab those 4 elements in the corner, we would do 1, colon 3 for the row and 1, colon 3 for the column. Now, just like NumPy assumes you start at the beginning, it assumes you end at the end. So you can actually omit the 3's and just leave it with a colon, which basically means take from the starting point all the way through the end. Let's see this in code. So if we do A 1, colon 3, comma 1, colon 3, we get our array of 5, 6, 8, 9. If we do the same thing but omit the 3's, so just A of 1, colon, comma 1, colon, we get the same thing. Now last, say you want this 5, 8 in the middle column. I'm actually not going to tell you this one. Why? Because I want you to think about it. And if you're smart enough to do so, comment below and tell me if you figured out easily how to index and just grab the 5, 8 from our array A. Batman has a mask, and NumPy has a mask too. Why? Because NumPy, like Batman, is a superhero. In all seriousness, masks are another way that you can grab specific elements from your array, but this time it's with numbers. So we've already talked about how you can grab any element by its index through broadcasting or indexing, but what if you want to grab elements that fit a certain mathematical criteria? So if we look back at our array A and we just type in A greater than 5, you'll see the exact same shape array, but with booleans as entries instead of numbers. And you can apply this array to your original array by putting the mask inside a bracket. So if we want just the elements of A that are greater than 5, we type A brackets A greater than 5. And of course, that gives back a one-dimensional array of 6, 7, 8, and 9. The creation. So quickly, I'm going to talk about a few different simple ways that you can create arrays quickly. There's a bunch of built-in things that automatically help you create arrays in a very efficient and fast way. For example, if you want an array of zeros, you just type in np.zeros with a tuple of the size that you want. In this case, 4, 5 is a 4 by 5 array of zeros. You can do the same things with ones. np.ones, 3, 2, boom, 3 by 2 array full of 1. If you want specific numbers on the diagonal with zeros everywhere else, you simply do np.diag with a list of numbers. It will create the appropriate shape for you. So a list of 1, 2, 3 will give us a 3 by 3 array with 1, 2, 3 on the diagonal. Let's say you don't really care what numbers you have in your array. Well, guess what? np.empty is what's for you. Just type in np.empty, give it a shape, and boom, you have an empty array, which in this case just claims it's 0. You want a random array for testing? np.random.random with a shape inside will give you a random array with numbers between 0 and 1. So here we did np.random.random of a 4x2. And last, you want something that looks like the identity, np.eye. And you can make that any shape you want as well. Sometimes you just want to combine a few different types of arrays together. So here's a couple of combining functions that Python has built in. First, we're going to create another array called B that's just zeros, and we're going to use our array A. First off, we're going to do an np.vstack. B stands for vertical. So what we're doing is vertically stacking in the vertical direction A and B. So that means the number of columns has to be the same, or else you're gonna get an error. There's also hstack, which is, as you can imagine, horizontal stack. That means we're taking A and stacking B horizontally to it. And this won't work unless your number of rows is the same. And you know how I remember that? HR, human resources. I don't know, it works for me. There's also a method called np.append. And you know what? It works almost the exact same. If you just stick in np.append of AB, then you're just gonna get a flattened array of all of the elements of A and all of the elements of B. But you can specify an access. So if you do np.append of A comma B with access equals 0, you'll notice this actually works the same as np.vstack. And if you do np.append of A comma B with access equals 1, now you're doing things on the rows, and it's just like np.hstack. In fact, with almost every single NumPy function, whenever there's an access keyword, access equals 0 usually refers to the columns, and access equals 1 usually refers to the row. Oh no! We've combined too many arrays and now we need to split them! The opposite of combining is splitting, and NumPy can do that as well. Just like we used np.vstack and np.hstack to stack different arrays together, you can use np.hsplit and np.vsplit to split arrays. Hsplit is horizontal split, so it's going to split down the columns to create different horizontal pieces. So that means the number of columns needs to be divisible by the number of splits that you give it. And that's exactly how these split functions work. You give it the array and the number of splits you want to split it into. So if we do np.hsplit of A comma 3, we're splitting the array into 3 different pieces. So now we have 3 columns. And similarly with np.vsplit, we do np.vsplit of A comma 3, so we're cutting it on the rows. You may have looked at these arrays and thought, those are exactly like matrices from my linear algebra class. That's because they are. Now I want to get into some linear algebra. NumPy can do mathematical things so fast. It's so fast. Matrices, arrays, tomatoes, potatoes. Anything you would want to do mathematically with a matrix, you can use NumPy for. Let's say you just want to take the transpose. np.transpose of A is how you would do that. Or, equally, and a faster alternative, is A.T. And just like you learned how to do matrix multiplication in your classroom, you can do matrix multiplication on NumPy. Just type np.dot and put in the 2 arrays you want to multiply together. And remember, just like you learned in your math class, in order to multiply matrices together, the number of columns in the first matrix must line up with the number of rows in the second matrix. There's a shortcut for multiplying matrices as well. Just do A and then the @ symbol and then A, and this will create the same multiplication. And by the way, if you ever want to do component-wise math with scalars, that works as well. Let's say you want 5 times 8. You type 5 times 8 and boom, you get out a matrix array where every element is multiplied by 5. You can also do division, divide by 2, or a scalar of 1/2 essentially. Or you can add, if you just add a single scalar to it, it will add component-wise. We can even run some statistics on our matrix A. Let's say we want the mean of all of the elements. We just type np.mean of our matrix A and it will spit out the mean, which in this case of course is 5. But let's say we want the mean across a certain axis. If you remember, axis equals 0 is down the columns and axis equals 1 usually refers to the rows. So if we want the mean down the column, all we do is specify np.mean of A, where axis is equal to 0, and we'll get 3 numbers back, 1 for every single column. Now we can do np.mean of A where axis equals 1 for the mean across the rows. Similarly, we can also do np.std, sexually transmitted disease, which, it stands for standard deviation. But it works the same way. You can give it the entire matrix A, or you can specify axis equals 0 for the columns, or 1 for the rows. And when it comes to linear algebra, there's actually a whole subpackage called linal, which stands for linear algebra. And this has all kinds of linear algebra things in there. For example, if you want your eigenvectors and values, you type np.linal.eig, and that will give you an array of eigenvalues and the eigenvectors associated with those values. Let's say you want the QR decomposition. Linal can do that too. np.linal.qr of A will give back two arrays, Q and R, for the QR decomposition of A. Let's talk about the singular value decomposition. If you've ever done that by hand, sometimes it can take a lot of work. But guess what? NumPy can do that amount of work faster than a speeding bullet. You just type in np.linal.svd and plug in your matrix A, and out pops your U. Out pops your singular values, and out pops your V. Boom! So fast and incredible. In this video, let me show you some examples of how to create random matrices in Python. So we import NumPy as np, and let's import random. First, let's just type np.random.random. And then we'll enter a tuple here. Let's make this 2 by 2. And it will automatically create a matrix with entries between 0 and 1. So we got 2 columns and 2 rows with entries between 0 and 1, as you can see here. Now, if we want to change the value range, we can multiply by twice the value desired and then subtract the value desired. So 10 times np.random.random. And let's make this one 2 by 2 again, and we'll minus 5. So if we want entries between -5 and 5, that's what we do. So here are the entries between -5 and 5. So if you think of it in this way, the max number it could be is 10 times 1, which is 10, minus 5, which is 5. And then min number it can be is 10 times 0, which is 0, minus 5, which is -5. Hence numbers between 5 and -5. Let's say we want numbers between 100 and -100. So we type 200 times, and we'll do a 3 by 3 this time. And here we are. Our random matrix C has numbers between 100 and -100 because we multiplied by 200 and we subtracted 100. So the max it can be is positive 100 and the min is -100. So there you have it. That is how you create random arrays in Python. Let's start IPython and import NumPy as np. np.empty is a good way to initialize arrays. So let's make an array called initial. np.empty takes in the shape as a tuple, so we'll do 1, 10. And let's go ahead and see what that looks like. As you can see, it's not really empty, but it's just filled with random data. Notice the nan, or not a number, that's in this array. So now that it's initialized, you can fill it according to whatever algorithm you are using. So let's just fill up each column with a number inside of this little for loop. And now initial is updated and filled. So there you have it. That is how you can initialize arrays using NumPy's empty function. This video compares NumPy zeros with NumPy zeros like. So we import NumPy, and let's first go ahead and create a random matrix A. Let's make this 2 by 4. So it should have 2 rows and 4 columns. So we have 4 columns and 2 rows. Now we are prepared to use np.zeros like, since it takes an array or matrix as an input. So let's make B np.zeros like with A as the input. And this will be the exact same size as A. So 4 columns and 2 rows. Now for the zeros, this takes a tuple of numbers for the size. So let's say 3 by 3. So we enter that tuple, and there's C printed out with 3 rows and 3 columns. And for reference, here's B and A again. So remember, B just takes on the same size as A, but C takes on this shape right here that we entered as a tuple. So 3 columns and 3 rows. Rows goes first and then columns. This video will compare ones versus ones like in NumPy. So we import NumPy, and let's make a random matrix A, np.random.random, and let's make it 3 by 2. So we put the tuple 3, 2 in there. So that means 3 rows and 2 columns. So here we have 1, 2 columns, 1, 2, 3 rows. To do np.ones like, we need to reference another matrix, which is why we created A. So it will take a matrix and create one of the same size, but fill it with ones. So here's B. Notice it's 2 columns and 3 rows, the same size as A. There's another way you can make ones matrices, and that's with the np.ones function. So let's make C np.ones. This, instead of taking another matrix, takes a tuple. So instead of 3 by 2, let's do 2 by 3. So there's to compare with B. We have 3 columns and 2 rows versus B that has 3 rows and 2 columns. We are comparing NumPy identity versus NumPy eyes in this video today. First, let's show you what the IPython description is for identity. So np.identity ? And here's the description. It just takes one number, n, for the size, and you can put a data type if you desire. So let's see what that looks like. Here we put a 3, and it spits out a 3 by 3 identity matrix. So 0, 1, 2, and 0, 1, 2 for 3 rows and 3 columns. Now let's compare that with the description for np.eye. As you can see, this takes a lot more parameters: n for rows, m for columns, k for diagonal index, and also a type and an order for either row major or column major styles, as you can see here. And let's go ahead and do a few examples with this. If we type in a 3, it works just like np.identity, so a 3 by 3 matrix identity. But we can put in a second number, and that will only give it 2 columns this time, so we're cutting off that last column, as you can see here. And now let's go ahead and add the k parameter to an example. We'll do a 3 by 3, and let's do parameter 1 for k. This moves the index of the diagonal up 1, so you can see the ones are now shifted up 1 diagonal. And lastly, if we did this 2 columns and -1 for the k parameter, it will make it shifted down 1.
Trill, trill, trill. Today we're going to talk about 2 NumPy functions, np.tril and np.triu. The tri stands for triangle, and the L and the U stand for lower and upper. So get ready, because it's coming at you fast.
So here we have a matrix A that I previously created, and let's zoom in and talk about a keyword called k. So when k equals 0, it refers to this main diagonal right here. And when k is a positive number, it's the upper triangular part, and when it's negative, it refers to the lower diagonals. You'll see what I mean when we do the application. If we type np.tril of A, k defaults to 0, so it's keeping that main diagonal all the way in the lower triangular. If we do k equals 1, then it's taking 1 above and keeping the lower triangular. K equals 2, 2 diagonals above and keeping the lower triangular. Now let's do np.tril with a negative k value. -1 means we're keeping just those lower 3 diagonals. -2 means we've indexed 2 diagonals away from the main diagonal. And of course, -3 just leaves us with 1 value, which is 6. Okay, now let's get into np.triu for an upper triangular matrix. We just plug that in straight, we get k equals 0, and we keep everything, including that, above.
k equals 1. Now we're just keeping one diagonal above the main diagonal and the numbers up above that. With k equals 2, we're starting 2 diagonals off the main diagonal and keeping everything up or above. Now let's do our negative k values with triu. So if we do triu of a with -1, now we're starting from one below the main diagonal and we keep everything above. With -2, we're starting 2 below the main diagonal, keeping everything above, and that's why you only see one 0 value there. How to use np.hstack in Python. We import NumPy as np, and now we will create some arrays to demonstrate with. To create an array, type np.array parentheses and a bracket to start the matrix and a bracket for each starting row. This is a 3x3 array we'll make, and end by closing the last bracket and parentheses. We'll press up on the arrow key here so we can bring that array up again, and we'll just edit it real quick to make a second array. We'll call that y. So let's change some of these values. 0, -2, 0. We'll just change this to make it distinct from the other one. So here we have our matrix X and our matrix Y. We type np.hstack with parentheses, and then you must make the entry a tuple, so do double parentheses. So here's Z. Notice the X array is on the left and Y is on the right because we typed X first then Y. Hstack is horizontal stack. So for it to work, both matrices must have the same amount of rows. So I like to remember HR, like human resources. Hstack works when rows line up. How to use np.vstack in Python. We import NumPy as np, and now we will create some arrays to demonstrate with. To create an array, type np.array parentheses, bracket to start the matrix, and a bracket starting each row. In this case, we will do a 3x3, and remember to end by closing the last bracket, end parentheses. We will press the up arrow on the keyboard to bring that up again so we can edit it to make a different matrix. So let's change some of these numbers here for -1 and 0. And we'll call this one Y. So here we have matrix X and here is matrix Y. We type np.vstack with parentheses, and then you must make the entry a tuple. So do double parentheses and put an X, Y. Notice the X array is on top and the Y matrix is on the bottom since we put X first then Y. VStack is vertical stack, so for it to work, both matrices must have the same amount of columns. So remember VC. VStack works when the column dimensions are the same.
Hello and welcome. We're going to start by using IPython and import NumPy as NP. First, let's go ahead and create some random arrays. So A is a 2x2. We're going to multiply that by 10 and subtract 5 so that its numbers are between 5 and -5, and we'll turn it into ints. Let's also create a random array b.random, and we'll do this one as a 2x1. And we'll also multiply by 10 and subtract 5, and b.astype int. And lastly, let's create C. C is equal to np.random.random. This one's going to be a 1x2 times by 10 minus 5. C is equal to c.astype int. Alright, so here's our array A, our array B, and our array C. Alright, for this first example, we're going to use A and B. Now remember, B is 2x1 and A is 2x2. And np.concatenate starts off with axis equals 0 as the default. So if I plug in A and B here, it will not work because with axis equals 0, they need to have the same number of columns because it works just like VStack. So there's A and there's B again. Now let's do np.concatenate with A and C. This one does work because C does have the same number of columns. So when it defaults to axis equals 0, it will work like np.vstack. number of columns need to line up. But with np.concatenate, if we give it a and b again, we can specify the access to be access equals 1. That means it's going to work just like np.hstack, so it's going to horizontally stack these together. And that way, the rows have to be the same dimension. So we have 2 and 2. 2 rows in A, 2 rows in B, and it stacks B right on the end. So there you go. That is how you can use np.concatenate in Python. Hello everyone. Today I'm going to show you how to use NumPy's append function. So let's import NumPy as np. And let's go ahead and create a random array A, multiply it by 10. We'll make this a 2 by 2 and we'll subtract 5 so that the numbers are between positive 5 and negative 5. And I'm go ahead and convert it to ints. And let's create an array B the exact same way. 2 by 2 and minus 5. And we'll convert that to as type ints as well. So here we have our random array A and our random array B. Excellent. So first thing, let's just put them in right away to np.append A and B. And you can see that it flattens both of them and puts them into a one-dimensional array. So here's A again and here's B. You can see A's those first 4 numbers and B's those last 4 numbers. Now let's change something up. Let's do A, B, and access equals 0. So now you can see it appended B onto the bottom. So here's A and here's B. So when access equals 0, they need to have the same number of columns. So because B has 2 columns and so does A, it allows it to be able to stick it onto the bottom. np.append A, B, and let's do access equals 1. When access equals 1, it sticks it on as more columns, so both have to have the same number of rows. So the dimension of rows have to be the same for this to work. This is the same as hstack, whereas access equals 0 was the same as np.vstack. But there you have it. That is how you can use np.append in Python. Alright, let's open up IPython and let's import NumPy as np. And we'll create a random 3x6 array we'll call A. And we'll quickly turn that into int types. Alright, so here's A, and now we can use A with np.hsplit to split A into subarrays. Let's try A, 3. And now we get a list of 3 different arrays. We cut the horizontal array into 3 different arrays, hence hsplit. Let's do this again. Here's A, and now let's cut it into 2 arrays. You can see now we have 2 3x3 arrays instead of 1 3x6. Split only works when the number of splits is a divisor of the amount of columns. This is because hsplit only allows you to split into equal portions. So np.hsplit cuts on the columns. And there you have it. That is how you can use np.hsplit. Alright, so first we import NumPy as np. And let's create a random 12x4 array that we'll call A. Now we can use np.vsplit on this array to split it into subarrays. So let's try np.vsplit A, 4. And now we get a list of 4 different arrays. 1, 2, 3, 4. We cut the vertical array A into 4, hence the V split for vertical. Let's do this again. Here is A. Now let's cut it into 6 arrays. You can see now we have 6 2x4 arrays instead of 1 12x4. Vsplit only works when the number of splits is a divisor of the amount of rows. This is because vsplit only allows you to split into equal portions. So always remember np.vsplit cuts on the rows. So there you have it. That is how you can use np.vsplit in Python. Alright, so we start IPython and we import NumPy as np. And let's create a random matrix A we'll do 6 by 6 by 6 between 50 and -50, and we'll turn that into ints. So let's go ahead and take a look at A. You see that it's 6 rows, 6 columns, and has a depth of 6. We'll do a.shape to see that, 6, 6, 6. np.dsplit a,3 will split on that last and final dimension. So now we have 1, 2 right here, and 3 arrays. Okay, to illustrate this point a little bit more clearly, let's take a look at the shape of A, and now we're going to look at the shape of each of those arrays that we split. So for A in np.dsplit a,3, let's print a.shape. Alright, so as you can see, it split on the last dimension, and we have 3 different arrays now coming from A, each 6 by 6 with a depth of 2. So dsplit always splits on the axis equals 2, or the 3D dimension. So that means the number you put in always has to be a divisor of that 3rd dimension. So there you have it. That is how you can use np.dsplit in Python. Alright, so let's start IPython and we'll import NumPy as np. And let's create a random matrix A. We'll make it 6 by 6 between 5 and -5. And let's go ahead and convert that to ints. Alright, so here's our matrix A. Split takes in the array, the number of splits, and the axis to split on. So we'll do np.split of a,3. This will default to axis equals 0. And let's compare that to a,3 axis equals 1. So axis equals 0 split across the rows. And we have 1, 2, and our third one up here. And axis equals 1 split down the columns. We have 1, 2, 3 down the columns. Let's look at A again. So depending on the axis, we split it here or here. Alright, real quick, let's take a look at the documentation. Again, we have our 3 parameters, an array, the amount of pieces to split it in, and the axis to split on. So let's do this one more time. We'll do np.split of a,2, axis equals 0, and np.split a,2, axis equals 1. When we do axis equals 0, it splits on the row, so it acts the same as np.vsplit. When we do axis equals 1, it acts on the columns, so it works just the same as np.hsplit. Now it's important to remember that the number of splits needs to be a divisor of the axis shape, and axis 0 refers to the rows, and axis 1 refers to the columns. So there you have it. That is how you can use np.split to split arrays in Python.
Array indexing is a very important tool, and I will introduce it here. We import NumPy as np since we will be creating arrays. For this example, let's make a random matrix A with numbers between -5 and 5. We don't need to import random, and let's make it 3 by 3. And real quick, let's go ahead and change this into ints so we can read it a little bit easier. So let's go ahead and bring this up again for reference, and for the first example, for any number that you want, go ahead and just type the index, so 0, 1, 2, 0, 1 will bring up that number, which is -1. Don't forget, when we do programming, we always start with number 0. For this next example, we do 1:, which is from the row in position 1, so the second row, all the way to the end. So -2, 0, -4, and the next row. And let's compare that with :1. That will be up to, but not including, the row in position 1. So up to, but not including this row right here. So it will just be the first row in this case. And let's see A again for reference. Let's do A 1:1. This will be the row in position 1, so at this -2 here, all the way to the end,
but from the column in position 1, so that 0 to the -1. And let's compare that with 1, 1, colon, which will be the row in position 1, but only the column from 0 to the -4, from 1 to the end. And let's do 0, colon, 1, colon 2. This one's a little bit interesting, but let's see how it works. So we do the 0th position to the end for the rows, so all the way down. And then we do limit it to the row in position 1 up to, but not including this position 2 right here. So just going to be 4, 0, -1. And lastly, I'm going to show you an example so you know how to get diagonals really quickly. So here's one more time. np.diag with A will return an array with a diagonal. You can change the index with a keyword argument if you want above or below. So let's do np.diag 1. So we get the 4 and -4 right there in this case. And for one more example, let's go the other way, A, -2, going below the diagonal, 0, 2 positions, right there to that 0. Array masking is a powerful coding tool, and I will show you how it works here. First, so we can make matrices, we import NumPy as NP, and we'll be using some random matrices, so we import random. We're going to make a 5x5 matrix. To create a random matrix, we type np.random.random and insert a tuple with the size of the desired matrix. Normally, np.random.random will automatically create random numbers between 0 and 1 for the entries, so we multiply by 10 and -5 to get numbers between -5 and 5. So there's our matrix A. And now we will create a mask. Let's call this mask, so we can keep it with what it is. And we'll do a mask everywhere where A is greater than 0. And we'll go ahead and print out this mask, and you'll see that it is the exact same size as our matrix A with Boolean values in every spot. True, where the values are greater than 0, and false, as you see here, where the values are negative. As you can see, the bottom row lines up perfect. Once we have a mask, we can type A bracket mask. This will be all the values of A that satisfy the mask. So here it is, all the positive numbers in A, and here's A once again, so you can compare. So there's the 2 and the 3. 0.019, and so on. If you have a giant piece of data that's in an array and you only need to see part of it, perhaps np.compress can help. np.compress takes in a 1D array of booleans, an array to compress, and the access to compress on. So if we type np.compress, we'll give it an array with just a single truth value, our matrix A, and we'll go ahead and specify access equals 0. And this returns the first row. Access equals 0 corresponds to rows, and since we put true, it just gives back the first row. Next, we'll do the same thing, give it A, but this time we'll do access equals 1. Access equals 1 corresponds to the columns. So there we have our first column since we gave it only one truth value. Alright, here's our matrix A once again, np.compress. You can also give it masks. So we'll go ahead and give it a mask here, A greater than 0. But be careful not to give it a mask that's more than one dimension, so we'll just take the first row of that mask. There's no number in the first row that is greater than 0. You have a 0, -6, and -5. And so, it doesn't return anything since those are all false. Okay, let's do np.compress. We'll give it the mask of A greater than 0 once again. And this time, let's give it a different row to base it off of. Let's give it the second index or last row, A in access equals 1. So it's going to take any column where the last row is greater than 0. So we have 1 right here that's greater than 0, so it gets that column. And 2 is greater than 0, so it also gets that column. All right, here's A once again. Let's do np.compress. We'll give it a mask, A greater than 0. And let's give it a single column to base it off of, so colon, comma, 1. So for the middle column, we're going to do axis equals 0. So it'll give us any row where the middle column is greater than 0. So 4 and 1 are greater than 0, so it will give us those two rows. Here's A once again, np.compress, A greater than 0, and this time we'll do colon, comma, 2 for the last column. But this time we will not specify an axis. When you don't specify an axis, it defaults to none and works on the flattened array. So now we have A greater than 0 in the last column. So since -5 was not true, we don't see the 0, but since 9 and 2 are both greater than 0, in the first row it will give us the last 2, so that's why we see the -6 and -5. Let's do that again, but base it off of the middle column. Alright, so the middle column is actually a very similar story. We have a -6, which is false, and then we have a 4 and a 1, which are both true. When you don't specify an axis, it defaults to none and works on the flattened array. We'll take -6 and -5 once again because 4 and 1 are both positive. So there you have it. That is a few examples of how you can use NumPy's compress function. Alright, so we have a giant matrix A and another smaller 2x2 matrix B, and in this video we're going to use np.where to change and manipulate the matrices how we want. Now np.where can take in up to 3 parameters: the array of booleans, an array of values to keep, and a replacement array. So I'm going to show you how this works with a few different examples. Alright, so let's get going with our examples. First off, we're going to do the matrix B. We'll type np.where and we'll give it a mask where B is greater than 0. And we'll hit enter there. And this may not seem like anything interesting at first, but let's take a look at B one more time. Alright, so what this gave back was actually the indices where the value is indeed true. So B greater than 0. So any index where B is greater than 0. You'll notice this 4 right here is indexed at 0, so row 0 and column 0. And that is indeed greater than 0. And this 1 at row 1, column 0 is greater than 0. So that's why it gives back a 0, 0 and a 1, 0. Alright, let's do a similar thing with A. But this time we'll do less than 0. So this is obviously a much bigger array, so there's a lot of indices. You can see that the indices line up with where the negative numbers are. And moving right along, alright, we'll do np.where of B greater than 0 to keep the values of B and replace any values where it's not true with -1. Alright, so B greater than 0. So the only places where B is greater than 0 is the 4 and 1. And so you'll see that those stayed the same. The 4 and the 1 are the same because we put B as the keep. -1 we put as the replacement. So anywhere where it was less than 0, so it didn't meet that condition, is now filled in with a -1. Alright, here's A once again. Let's do np.where A is less than 0. We'll keep A and we'll replace it with the value 100. So every time it's less than 0, it stayed just like the original A, and anytime it's greater than 0, so it didn't match the condition, it was replaced with the number 100. Now the replacement doesn't have to be a single number. You can actually give it an array of numbers. So let's go ahead and move along to that. So we'll do np.where, we'll give it B greater than 0. We'll keep B if that's the case, and we'll replace it with a different and new array. So B greater than 0, we keep B if that's the case, and if not, we replace with this array on the end, just full of zeros. And I didn't have to put all zeros in that case. So that -2 and -1 are now replaced with the zeros in that second array. And to illustrate this one more time, we'll do np.where A is greater than 0. A is going to be what we keep if that's the case. And our replacement will be a random array that's the same size as our original A. So if a is greater than 0, then we keep the original a, and if it's not greater than 0, we replace with a random number. So remember all those negatives at the beginning? Now we have a 0.708, a 0.406, and so on, but the positive numbers are still the same. So there you have it. That is how you can use NumPy's where function to manipulate arrays how you desire.
Hi friends, it's Rylan here, and we're going to be learning some of the fundamentals of statistics. That's right, we're going to be learning about 3 things: mean, median, and mode. Together with my friend Sam from Python Basics, I'm going to help you learn how to take these 3 things not only in one dimension, but in multiple dimensions. Alright, so I'm going to start IPython here. And I'm just going to paste in some data that I have, and let's look at the length of this data, and wow, it's 36. So yeah, that's not something we want to take the mean by hand. So if we import NumPy as np, then we can type np.mean of the data, and voila, 4.36. That was very fast and awesome, and we didn't have to do it by hand. But let's say data is an np.array, and let's go ahead and reshape this as a 6x6. Let's say it's has multiple dimensions. So data here is now 6 rows by 6 columns. We can do np.mean of data the same way, 4.36 as we saw before. And we can take the mean of the data on a specific axis. In this case, let's do axis equals 0. And now we have the mean of every single column. So going down the columns, it's adding those together, dividing them by 6, and that is the array that we get left over. Now let's do axis equals 1. Okay, so this one is taking the mean on the rows. So it's taking the mean on every single row. Okay, now I'm going to pass over to my friend Sam from Python Basics.
Hi everybody, this is Sam with Python Basics, and Rylan has asked me to join you guys in explaining median. So first of all, nice to meet you guys, and Rylan, thank you for this opportunity. So let's just go ahead and get started. So alright, I'm using the same list that Rylan has, and I'm going to talk about median. So, quick lesson if you're not sure. Median is the midpoint of a collection. All right. Now it's not average, it's not mean. That may look like the average, but let me show you. That is an even. Let me show you an odd collection. So if this wouldn't be 1. So, alright, it is the midpoint. So alright, let's look at what median does with our list. Data. I get 4. So let me just show you real quick why. Let's do sort data. So alright, the midpoint is literally right in between 2 4s, so that's why. So alright, now let's put data back in memory. Okay, it's our not unsorted list. So now I want to show you a argument, the axis argument that was in median. This is where NumPy becomes very, very handy and very, very powerful. So alright, data, NumPy array. There we go. So now I'm going to change the shape on this so we can see what all this does. Data.shape. Let's do 6x6. There we go. So alright. Median data. Now we're going to take our optional axis. So let's look at what this does first. It accepts 0 or 1. 0 does our columns, says I want the median this way, and 1 goes the other way. So let's look at this. Boom. There we go. So this is a quick crash course in NumPy's median, and this is where this gets very powerful and very handy. So I want to tell you guys, thanks for having me. Rylan, I appreciate this opportunity. This was very cool and very awesome. Hopefully we can keep doing stuff like this, but thanks guys, thanks for having me. Hope you got something out of it. Hope you enjoyed it. Hope to see you guys next time.
Okay, now let's look at our data again. It's already 6x6, and we'll do from scipy.stats import mode. We're going to learn how to use this mode function. Let's just type mode of our data, and you can see what results out is actually the mode of every single column. So in the first column, you see there's 2 3s, and it writes the number 3 as the mode with 2 in the count array. And you'll notice if you pay attention to this, it actually will give you the minimum if there's more than one that have the same count. So that's why you see a couple of 1s there. And now let's do mode, and let's specify an access. We'll do access equals 1. So the previous one defaulted to access equals 0, and this one, access equals 1, is now doing the mode across every row. So you'll notice in the second row there's 2 7s, and that's the mode. So in the second entry it's a 7, and in the count array the second entry is a 2. Now let's say we want to take the mode of the entire array as it's flattened, or in other words, take it on none of the axes. There's 2 different ways to do this. We can type mode of np.ravel of the data, which if you look at np.ravel of data, that's just flattening the array, and that gives us the mode is 4 and that the count is 6. Or equally as powerful, or in the exact same way, you can do mode of data of access equals none, and that data was still the 6x6 array, and it spits out with access equals none the same thing as it would with the flattened array, meaning mode is 4 and count is 6.
Array and matrix multiplication. In IPython, we import NumPy as np. To define an array, we type np.array, parentheses, bracket to start the matrix, then another bracket to enter the first row. After each row, close with a bracket, and at the end, we close the entire matrix with one more bracket, and finally, we close our parentheses. This is what the array will look like when you print it out. And let's go ahead and save this array as a 3x3 array called X. Here we are going to reshape our X matrix to be one long matrix that is 1 row by 9 columns. This is important to do sometimes because in matrix multiplication, the dimensions need to line up. An easy way to remember how to know if the dimensions will work is to look at the number of columns of the first matrix, or second dimension number, and the number of rows of the second matrix, or first dimension number. Those numbers need to be the same for it to work. Now I have defined a matrix Y so we can see multiplication in action. Notice the X is shaped 3x3, and this Y I'm making is 3x2. Since 3 equals 3, we can do this multiplication, but only if we do X first, then Y. To multiply, you can use the @ symbol. X first and then Y. If we did it the other way, the dimensions would not line up.
So you need to sum a list. Well, what are you going to use? np.sum or the built-in sum function? In this video we're going to talk about the difference between np.sum and the sum built-in function.
So I'm going to import NumPy as np, and I already have a matrix A that I created earlier, so here's that matrix A. And let's type in the built-in sum function that comes already in Python without importing anything. So we'll type sum of A, and we get 1, 4, -2, and 4, which is adding down the column. So that's the sum of every single column.
And if we do np.sum of a, we get one number back because it's the combination or the sum of every single element. Now with np.sum, you can give it different parameters. So let's try axis equals 0. Now you'll notice axis equals 0 is the same thing as our built-in sum function, so it's adding down the columns. But what if we do np.sum of a with axis equals 1? Now we're getting the addition across the row, so you're adding every single row. But those aren't the only parameters. Here's a again. Let's do np.sum of a, axis equals 0, and I'm gonna give it this parameter called keepDims equals true, which is telling it to keep the dimensions. So with axis equals 0, it was adding down the columns, and with axis equals 1, it's adding across the rows. So you'll see we have a row vector and a column vector that got spit out when we did keep dimensions. Here's a one more time. We'll do np.sum of a, axis equals 1, and I'm gonna give it a different keyword that says initial equal 5. Now let me compare this to np.sum without the initial equals 5 so you can see the difference. Basically with initial equals 5, it means you begin adding from that initial number. So the initial equals 5 is 5 more than without the initial parameter because you're just adding 5 to every single element in the sum. Okay, here's a again, and let's do a different parameter of np.sum. We'll do a, d type equals float, which of course just means you can change the type. You see that decimal spot there? You can also use this with a different axis, of course, to give it float types as a return type for each element. Now let's take a look at the documentation, and you see we've covered all of these parameters here, and that is the main difference between the built-in sum and np.sum. np.sum can do everything the sum can, plus it has all these other parameters that allows you to do so much more.
Ravel, 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 np.ravel. Basically comparable to a rave at a crazy party. But this is a NumPy function that is quite useful because it unravels what you have. Why didn't they call it unravel?
np.ravel is of course a function of NumPy. So here I have a matrix A that I created before, and what we're going to do is type in np.ravel of the matrix A. And you can see that it created a flattened array where it went one row at a time. So you see the -2, 2, 1, and 2 was stuck in first. But if we do np.ravel of A with the keyword of F, you'll see that it does the same thing but columns first. So -2, 0, 1, 2 goes in first, followed by 2, 1, 1, 0, and so on. So let me type np.ravel with a question mark so we can pull up the documentation. So as you can see, it takes in an array and an order. The orders can be either C, F, A, or K. It defaults to C, so that was the first example that we saw, and then F is based off of the columns. A means to read in the elements like Fortran, and K means to read in the elements in order they occur in memory. NumPy has a function that should remind you of a tile floor. In fact, it's called np.tile. That is, if you import a NumPy as np. This is a pretty awesome function that allows you to take a matrix and tile it as many times as you want. So let's get into this NumPy tutorial. Let's start IPython and we'll import NumPy as np. Quickly, I'm just going to create a random matrix X that's going to be 3 by 2. Make it type int so you can read it a little bit better, and there is our matrix X that we're going to use this tile function on. So if we type np.tile and give it X and just some number 2, you'll see with our original X, 2 of X's stacked to the one to the left and one to the right of each other. So it's adding more columns. So here's X again, and let's do np.tile, and this time let's give it a tuple. You can give it a tuple specifying the row, comma, column. So now that we did 2, 1, you'll see that it's adding an additional X, taking X and copying it down as more rows. So you can see this a little bit better. Let's do np.tile of X, 2 by 2. So this is going to take the entire array X and make 2 by 2 matrix out of it. So you can see there's 2 X's per each row, or there's 2 X's per each column. Okay, here's X again. Let's do np.tile of X with 0, 1, and just to show you that this is going to give you back an array that's empty. And going right into our last example, here's x again, and let's do np.tile of a 2 by 3. So now we've added an extra entire matrix x on the row, and there's 3 columns of x, and there's 2 rows of x. So it's copying x 3 times in the column direction and 2 times in the row direction. So that's what that 2 by 3 tuple is doing that you give it, and that's how you can decide how to tile this matrix out into a lot of different matrices to make one giant matrix. So there you have it. That is how you can use np.tile to tile your matrices and expand them for your personal use.
So here we have a random array A that I created earlier. np.roll is a NumPy function that allows you to shift arrays by as many indices as you desire. So let's jump into this example, np.roll of a, 1. And there you have the output of that, which is just the same shape array, but this one is now where the 10 used to be. 10's been shifted over 1, 3's been shifted over 1, 12 is shifted over to where 14 was, and 14 has been shifted down to where this 11 was. So as you can see, everything has been shifted over to the right 1 index. Okay, let's see A again. This time let's do np.roll of a, 2. So now we've shifted everything over by 2 indices. So this 13 has been 1, 2, up to that spot. The 10's been shifted over 1, 2 to this spot. 8's been shifted over 1, 2 to this spot, and so on and so forth. Now, because of that parameter 2, everything has been shifted over 2 times. Now, you might be wondering why this is useful. So let's go ahead and show you an application. Suppose you have an array of points and you want to approximate the derivative, or in other words, the step at each point. np.roll can help you to do that. So what we did here is dA is the difference between every single A point. Now, make sure to ignore the first term. If we are finding the difference in 25 points, then there will only be 24 differences. The first term is the difference between the first and last point. So it's the difference between 10 and 1. And that's not really applicable to this derivative thing that we're doing. So the best way to ignore that is just use your array slicing to cut off the first point. So this -7 corresponds to the 10 and 3. So from 10 to 3, we moved -7 steps down. The 3 and 8 correspond to this 5. From 3 to 8, we moved 5 steps up, and so on and so forth. So this allows you to see the steps between each point. So there you have it. That is how you can use NumPy's np.roll function in Python. Here we have a 10 by 10 random array I created called A. So let's say you have a giant array like this A we have here that you want to send to a friend or save as data for later. NumPy's np.save will allow you to do this. So before we do anything, we can take a look at the documentation. We need a file name and the array as inputs. There are also 2 more parameters called allowPickle and fix imports, which you would only be interested in changing if you are worried about security or need to export in a format that is compatible with certain functions in Python's older version or Python 2. But for us, it will be as simple as giving a file name and the array to save. So we type np.save sample.npy, A. The .npy is the standard extension for NumPy arrays when they are saved as files. I saved this on my desktop, so let's see if it's there. Excellent, just like we wanted, it's saved on the desktop. That's the file we just created. Alright, so to load a saved NumPy array or pickle file using NumPy, we need to first import NumPy as np. So import NumPy as np. Next, we'll just say a equals np.load, and in quotes we'll put the file, so sample.npy. And now let's go ahead and see what A looks like. Excellent, this is the same array we saved in the np.save video, and it loaded so fast and so easy. So here's the file we loaded sitting on the desktop. You can also include the file path as part of your string if you're running code that is not in the same folder as the array you are trying to load. And here's just a quick look at the documentation for np.load. You can use np.load to also load np.z files, which can also be arrays or other Python pickle files. So there you have it. That is how you can use NumPy's np.load to read in arrays. So let's import NumPy as np. Then let's go ahead and create a bunch of arrays. So for A, we'll do random.random. For B, let's do np.zeros. For C, let's do np.ones. In D, let's go ahead and make this an empty array, so np.empty. And let's end with a np.eye. np.who will allow us to see information about all current arrays we have. All you have to do is type np.who, and it will send this to the screen. So as you can see here, it gives us the name, shape, bytes, and data type for each of the arrays we are currently using. This could be very helpful for debugging purposes, especially if you have a shape error. So there you have it. That is how you can use np.who in Python. Let me show you a great way to compare and test outputs in code. I like to use np.allclose. In IPython, we can see some of the parameters for this function. So we have the two things we're going to compare, A and B, and you can set different tolerances. And there's a parameter for what you want to do with nands or not A numbers. So that will just be a Boolean operator. And you have the relative tolerance parameter and the absolute tolerance parameter, and you can see the notes to learn more about those. This returns a bool value, so either true or false. So let's go ahead and do an example. For this first example, let's put in just two obvious things that we know will be different, so 5.5 and 5.4. And it returns false. But let's do something a bit harder. We will do 1 and 0.99999, a lot of nines. And it returns true. This is because your computer cannot tell the difference, and we won't get into details of why that is here.
To look at my YouTube channel's numbers, we're actually not going to go to youtube.com, because what I did previously was download my data as a CSV, and I am currently reading it in and running this code so you can see it as a Python pandas data frame. So here's our data frame with the date, time, watch time, minutes, views, subscribers, thumbnail impressions, and impression click-through rate. And now let's go ahead and plot the watch time minutes for the last 365 days. And you can see the plot here. This is exactly what it looks like on my channel's analytics page. And now what we're going to do is see if we can use this data to predict the future of our channel. So first I want to just try a linear regression just for kicks and giggles. So let's go ahead and create the model, and now I'm going to plot that against the actual data. And there it is, our linear regression, and quite frankly I don't think this is a good model because it doesn't look linear. So let's try something else. Next, I'm going to do np.polyfit to create an exponential-like function with these np.exps. So now let's run that model and see if it fits better. Ooh, I like the fit of this model better. And in fact, why don't we use this to try and predict what we may expect in the future if this trend continues? I have already written a function to do this. The function I wrote is called future hours, and what you plug in is the number of minutes, and it will tell you how long the model expects you to take to get to receiving that many minutes per day. So for example, we plug in 1,000, it says we will hit 1,000 minutes a day in 103 days. The green line is the future prediction of what it expects the trend to continue to be like. Let's go ahead and plug in 5,000 minutes a day. So this will take us 336 days to start getting 5,000 minutes a day. Now everyone's interested in the 4,000 hours watched mark. So let's do 4,000 times 60. and that says it will take us 897 days, or over 2 years, to hit that mark in 1 day. Now, I'm gonna divide that by 31. So this is gonna be the amount of minutes we would need every day in 1 month to get 4,000 hours in that month. And it says it's going to take 399 days, which is over a year, to be able to hit 4,000 hours in a single month. Thank you for watching the video. I hope you enjoyed it. If you haven't already, please click subscribe. Here are 2 other videos that I think you'll enjoy.